Okay, in the last session, remember we looked at the forces, the not in line, where we had to come up with the resultant of what was going to happen. Now we're going to look at an electrical field situation where we're talking about an electric field that exists between two things, right? If, for example, we took let's say two square pieces of metal like that, right? And we connected a battery to these guys over here. This is the negative side, that's the positive side, right? So what have we got? This side is negative. There's no current flowing here, right? So there's no flow of electrons. So what is happening is that all of these electrons are sitting here, aren't they? Right? And they have been, let's say, taken from here. So we've got our positive charge sitting over there. All right? Well, that's logical, isn't it? Which means that if we look on the surface of this one here, right, we've got, if we use our previous thing, remember we've got a parking spot there, and we've got an electron over there. I'm just looking at these two there. That means that I've got a field line there, haven't I, between those? Which means that between these, I can draw field lines, right? Okay. How many of them? Whatever. That's not important at the moment. Just the concept is that we've got a charge there and a charge there. So we can have, because it's an electron and let's say the proton over here, that side, we've got a charge, which means we've got a force between them. That's what I'm drawing, right? Now, what is an electric field, right? Let's just look at how it's defined, right? An electric field is a region of space where a charge experiences a force. The force exerted by an electric field E on a charge Q is F equals QE. Well, let's write that down. F equals QE, which if I rearrange it, E is equal to F over. And some books use little q, some books use a big Q. All right? I'm just going to make it interchangeable because let's just get the concept of what's happening here, because that's the important part. Do you know what? The numbers and the calcs, they come with the practice. It's actually what are we looking at and how do we apply it? What does it mean to us? Well, what do we measure force in? Newtons, and charge, coulombs. So an electric field strength over there, E, is measured in newtons, coulomb, minus 1, newtons per coulomb. That's what we're measuring E, the electric field strength in. It is, just to recap it, is a region of space. It's in here. Let's just isolate this so that we've got the definition. It's a region of space. It's between here where a charge experiences a force. So now they've said a charge experiences a force. What do they mean? Actually, what they mean is I drop a positive charge in there. What happens to it? The charge that I put between these two over here, I put what's called a positive test charge. Okay? A positive test charge. Okay? Between these two. In this space. This space could be a long way apart, obviously, right? But it's in that space. So we hang a little positive test charge and we look at what happens to it. All right? The force that it experiences defines the electric field. So in this case here, what is this guy going to experience? It's positive, positive, it's going to be pushed that way. So between these two plates, these two metal plates, or between other things where there's an electric field, if I hang my little positive charge, it's being pushed that way, which means that that's my electric field running that way to that way, plus to minus, right? Once again, some kind of questions. You can be said, right, there's a plate, right? And we hang a test charge, and the test charge is moved that way. Draw the field between the two, right? Well, we know, first of all, how do we do it? We say, this is a positive charge, so we label it. Positive is being moved that way, which means this side must be positive, and this side must be negative. It's being pulled that way. Note in this case that it's got a push and a pull, right? So that's my negative space, this is or my plate, and therefore I can draw my lines of electric field, which is the direction indicated by the way a positive charge would move. Right? As I said, remember, this one and this one are exerting a force on that. Remember, it's the same as a charge, and a charge put in the middle. That one pushes it, this one pulls it. The net result is to move it that way, with an acceleration, obviously, right? Now, what is the next part of this? Okay, we've got the field line, okay, and we say, all right, let's have a look here and say, okay, now where we've got charges, right? We've got various charges, Q at A, B, C, right? So we're now going to look at the electric field strength due to the charge. Let's first of all take a charge over here of A. Okay, let's say the charge at A is 6 coulombs. All right, just for argument's sake. Okay, it's 6 coulombs, right? What would the field strength be over there? Okay, if we said that there is, let's say it's 200 millimeters away. What do we say? We say electric field strength is force over charge, right? So we've now got to say, right, what happens over here? What do? We've got our test charge there, haven't we? Of 1, right? We now need to develop a way that we can manipulate or work this formula to instantly get the answer to it. So what do? We can do some substitutions in here, right? Let's look at, first of all, we know that F is equal to Q times E, don't we? Right? We also know that F is equal to K, Q1, Q2 over R squared, right? Now, if that's a test charge and I put it there, the force at that point, right, is going to be the same as being experienced by that formula, correct? So I can put them equal to it. Q, E is equal to K, Q1, Q2 over R squared. Now I can make Q, the test charge, is that one. It's the same charge. So my electric field strength is K, Q1 over R squared, isn't it? Because this Q here and Q2 are the same. Q and Q2. It's my test charge that I'm putting in there. It essentially cancels out, doesn't it? So my electric field strength at that point there is given by this. It is going to be 9 times 10 to the 9 multiplied by Q, which is 6 coulombs over, and in this case it's going to be 0.2 squared, which is quite a big force, 10 to the 9 times 6 divided by 0.2, it's going to be equal to 1.35 times 10 to the 12. Okay, newtons, which is a pretty substantial force. Make no newtons per coulomb, my bad. Right? It's the electric field strength. Right? Straightforward. Let's just go through this derivation of the formula once more, because I think it's important to understand it. It's very similar to the one for Newton for gravitation on a planet, if you think about it. We're just cancelling out the one. What are we saying? We are saying this, right? Just page, all right. What are we saying? We are saying that I have got a charge over here. Let us look at it now in the sense. We've got P, okay, and we've got Q, point C over there. We've got point B over here and point A down there, right? And we said that this is plus 1 coulomb. This over here is minus 2 coulombs. This over here is plus 6 coulombs. And they want the, just let me put in some dimensions, 1 centimeter. Over here is 2 centimeters. And over here is 4 centimeters, right? Right. First of all, let's just go back to this derivation of this formula, shall we? Let's just page up onto it there. Right. So fine. The electric field strength, right, is given by that's a force experienced by a test charge. So at any point, we've got a force, okay, is equal to E times Q, which means my electric field strength is force over, and this is the charge on the test charge, right? So it's the force which, if we take now, remember, we've got an electric field, we take our charge and we drop it in, okay, to the electric field. And we measure the force on it and which way it goes, attraction or repulsion, but the direction is going to be the big issue here, isn't it? So what do? Is we say, right, we drop it in, so we measure the force on that, right? And the electric field strength is a measure of newtons per coulomb, the force divided by the charge. So let me now call this, I just want to change this into here. I'm now going to call this Q test, right? Everybody should be happy with that. So therefore I can go back and say, right, the force is equal to E times Q test, right? But similarly, we know the force between charges is Q1, Q2 over R squared, isn't it? But Q2 in this case is, because what did we do? We remember we had our little test charge. This was plus, and this was minus. The force on there was that way, pushing it that way, repelling, and pulling from this side, from the negative side. So it was moving it that way. And how did we work it out? We said, well, what did we do? Remember on the line one where we had these guys? We first of all said, you pushing that way, you're pulling that way, the resultant is that way. Same thing, charge here, charge there, that's pull. So we've got two separate ones. This charge is Q test. It was the Q in the middle. So what have we done? We say, right then, therefore, I can change U to Q test. But this force must be the same force, right? Same as the gravity situation. We put them equal. E Q test must be equal to K Q1 Q test over R squared. I can now take Q test and we can cancel it out, guys. So we then end up with E is equal to K Q1 over R squared. That's the formula there that we've got to use and remember. All right? let's look at an example. This one is quite a nice one. Okay, they've asked us, what is the electric field strength at P? We need the electric field strength at P. Okay, well, what are we going to do? It's going to be a combination, isn't it? How many charges are adding to this? Well, we've got this one, and this one. They're all going to have an effect at that point, aren't they? Let's split them up into the colors. First of all, let's look at the charge C, right? Here. This is a, remember, this is a plus. Our electric field strength here is what would happen to a positive charge, right? So here we've got a plus and a plus. So from C, we're going to have a force there. I'm going to call that electric field strength due to C, right? So my arrows will be going that way, pushing me away, right? Let's have a look at the electric field strength due to B. Let's do it in red, okay? That is a minus and it's a plus. So electric field strength at B is going to be pulling it back, isn't it? Okay? Because B is a minus, this is a positive charge, it's going to be pulling it. So the B is going to be cancelling out some of the one above. Let's now go to A, okay? And say, right, A is plus, that's plus, so the electric field strength at A is acting that way, right? Now we go and work them out independently, okay? What is C? So we say, right, electric field strength at C is K, 9 times 10 to the 9, times Q, which is plus 6, okay, Q over R squared, and my radius here is going to be equal to 1 centimeter, which is 0.1 squared. So let's have a look at that. E at C because of U is going to be 9 10 to the 9 times 6 divided by, and it's it's 1, it's 1.1, was that divided by 0.1 equals that 5.4 times 10 to the 11. 5.4 times 10 to the 11. Okay? So that's that guy. 6 coulombs, yep. Right? Let's have a look now and calculate the red one. The electric field strength due to B. Okay? Now EB. Okay? Remember, that one is, okay, the black one was up. Now let's have a look at the red one. It's going to be 9 times 10 to the 9 times 2. Okay? If you leave the charge, the sign out, right? You can put it in, call that plus and call that minus over, and the distance is now going to be 3 centimeters, right? Which is 0.3 squared. Now let's have a look. That's 9, it's 10 to the 9, times 2 divided by 2 times 10 to the 11. Okay, and my field strength is newtons per coulomb. I should write it in every time, newtons per coulomb. Now you could say to yourself, okay, I'll take that as minus, or we just say down, right? And the last one is the green one, which is the electric field strength, electric field strength due to C is going to be 9 times 10 to the 9 times 1 divided by how far? 4, 6, 7. 0.7 squared. Agreed? Okay. Silly me, look what I've done. I've actually, can you see in the conversions here? Now, you know, that happens all the time to people. It's not centimeters. I converted. It's 0.01, isn't it? And it's 0.03. And over here is 0.07 squared in each case, right? So let me just change that. Okay, that's going to change that to a 12, isn't it? That was silly. Okay, 12. This one is going to be red, is going to be 12, right? Can you see what happened there? I made a mistake with centimeters. We've always got to do that carefully. Otherwise, we make the same mistakes, and we all make them. Okay, so let's go to a green one. Okay, that's 9 times 10 to the 9. Okay, 9 times 10 to the 9 equals that. Well, it's times 1. Divide by 0.07. Divide 0.07 is going to be 1.84. Okay, times 10 to the 12 newtons per coulomb. And which way is she acting? It is up, positive, negative, whatever. How do we find out the resultant? Well, the resultant is, all we've got to do is we've got to add them together. Let's just go to black. So let's get our fields. We've got 5.4 minus 2, so we've got 5.4 up, 2 down, and the last one was 1.84 up. What's the net of those lot? It's quite straightforward. We're just going to use the sign and subtract. That one we're going to be subtracting, aren't we? So it's 5.4 minus 2 plus 1.84 is going to be equal to that. 5.4 minus 2 plus 1.84 is going to be 5.24 times 10 to the 12 newtons per coulomb. Okay. Can you see what we've done there? Apologies about the thing, but I guess let that be a lesson to us all. Let's just recap what we've done. We've done electric field strength. Okay. In here, we are looking at what is happening. How do we measure the force or the electric field strength in some number, and it's called newtons per coulomb, right? It's essentially a measurement of the force experienced by a positive test charge. So when we are given certain charges, right, if you remember, we did the little derivation of the formula, and it showed that, like, very similar to the Newton's gravity one, okay, we had the value of the test charge disappearing. It cancelled out. So when we've got a problem like this, same situation, let us, for example, say we had this. We've got a charge at A, a charge at B, a charge at C. And they want to know the electric field strength at C, right? Let's say that this is plus and this is minus. So what do? We go and drop a test charge there of A plus. This one will be pushing away. This one will be pulling up like that. And we do exactly the same. The field strength is a vector. So we can work out newtons per coulomb there, newtons per coulomb, get the angle. What do? It's a vector at an angle, so we do the components. We're going to end up with to the right, to the left, and to the top, right? Essentially giving us a situation where we can work out a resultant. Why? It's a vector. Why is it a vector? Because it's indicating the direction of movement and the force on a particle, isn't it? Because we said that the force, right, was equal to, okay, so E is a force, okay, because E is F over Q, newtons per coulomb. That is giving us the direction and the magnitude, because it's either attraction or repulsion, which is in fact the the directionality of it. Okay, so it's very similar to the previous one. Okay, I'm going to do load up some more problems in this. Okay, I'd like to sort of in the next one we're going to talk about magnetic fields. Okay, and how they affect, because what we're building up to is we're building up towards an understanding of putting together motors and generators, which, given the power scarcity, not only South Africa but worldwide, there's problems with it. We have a situation of we need to be able to get a generator. Okay, and we'll be talking about how do we do these things and how could we design one and stuff like that. Now, that's going to be that one. As I say, I'm going to come back, stick some more examples in all of the sessions that we do. So we're going to move on to magnetism next.